Okay, we are at noontime now. So number one, first announcement. I checked the score for quiz 3A and 3B. Okay, and then they both have very low average score. So I decided that for both of these quiz, we add one more attempt for each student. Is that okay?
Yeah, it's okay. Sounds good.
Okay, so try harder. Okay, anyway, that's number one thing I would like to announce. Second one, I would like to look at this programming assignment 4. Okay, this one so far, I didn't see any student who actually scored, give the perfect answer. Okay, and then I think that some people still have problem modeling it. Okay, this one is more creative assignment. Okay, it's not just copy the code from me that it should be fine. So this one a little bit harder, but to figure out the workspace is very important. For example, you want to sell a robot to some company, right? So such as, okay, if you have the country robot, okay, something like this, and this move, okay, and usually this kind of large country robot is used for shipbuilding center, so the robot can move here, okay, and it can go up and down. So the maximum working space will define how much area you can actually work on it, okay, where you can work on it. So it's very important. So workspace has always been a very important topic, okay. So the one that we are looking at, okay, let's look at this kinematic diagram. Okay. This one you're looking at actually is a solution given by one former student. So it's it actually is a student that actually very outstanding, okay, Louis. I think he eventually go to study PhD in math or something, okay. I forget his outcome, but I remember that he has a master in math, okay, or something like that. So anyway, this kinematic diagram, the base is here, okay, you rotate, so let's just look at this center of the joint here. So this point, since the rotation, you make a whole circle, right? But it's up in the air because you have the base length this much high. So it's something like a circle, but you actually hear from the base, something like this, okay? So because of that, okay, then second one, you actually have the rotator. So that's essentially a certain length. So this one, you actually make a circle around it. So for each point, you make a circle around it, and then you go 360 degrees, okay? Eventually, the workspace become a donut shaped. Stop here, okay? And he make use a PyLab to use some sort of color temperature to draw this one. It's a perfect drawing, this one, okay? So if you can figure out it's a donut, it's something like this, okay? And donut happen in many of the robot, okay? In many of the robot. Good morning, okay. Any questions so far?
No, sir, we are good.
So in terms of study for this one, number one, you need to figure out the kinematic diagram like this, right? Second one, you based on this kinematic diagram, you go on to the calculate the masses theta1, theta2, A1, A2, A3, okay, whatever number you have, and then use the model. You will come out with some equation, and that you should be able to see already a donut-shaped data. Okay, that's the workspace. So here, when you study the robot, there are always two spaces. One is the workspace. Workspace is where your robotic finger can touch the maximum range that you can touch by your robot arm or robot fingers. Okay, that's called workspace. Another one is the joint space. Joint space is the variable space of the theta 1, theta 2, theta 3, and the D1, D2, D3. Okay, those are joint spaces. So you may use the joint spaces to control where you can reach. Okay, that actually is one thing. You can also use the plane, the workspace location, to guide your variable in the system, so that you actually would drive to the desired location. Okay, so we do mathematical planning in for robotics. Primarily is either used from joint space to find a solution space where you should be, or backward from the workspace to find what are the joint variables should be. Okay, and make plan to do it. Okay. So we study so far are actually working on the loop, okay, feedback loop. Let's go back. Okay, so today's topic. There's an image. Okay, we'll talk about images later. Now this dynamic boundary, that's too far. Let's look at this architecture. Okay. So architecture, robot control architecture. Okay, how important is this robot control architecture? Okay. I would say this is the most important topic right now. Okay, why I'm saying this? Because you have drone, you have autopiloting car, you have many things that are actually related to robot. Okay, so in the past, you become a computer science student, right? So core computer science courses, they tell you that, oh, you need to study algorithm, you need to study data structure, you need to study operation system. Okay, you need to study programming language, like the one that I teach, 46K. Okay, you need to study networking. Okay, you need to study database. Okay, and there's another course usually is a core course, that's computer architecture, right? Some students hate it because it's a hardware course, but that's not good. Okay, because the computer architecture always driving the technology. Okay, why I'm talking about computer architecture? Because this is 20 years ago. It's computer architecture. Nowadays, you should study robot control architecture. This is the computer architecture of the next generation. That's why you take this robotic course. Okay. So 20 years ago, you study like my student or myself, we study RISC-V machine. We are happy, right? And at that time, people are actually computing in in the how many gigahertz of the CPU. But those days are gone. Okay, nowadays those CPU designs are like a piece of cake. So some company like Microsoft or Apple, they are able to license the ARM core and then build a machine, right? Build a machine. So CPU design is no longer the main topic of the hardware. Nowadays, it become computer architecture. Okay, it's a robotic architecture, and robotic architecture is different from the regular computer architecture. Regular computer architecture, you do what? You do instruction set, right? But nowadays, it's not instruction set. Okay, it combines a lot of things. Number one, computation itself. Okay, so by computation itself, you may have neural network, right? You may have neural network. So neural network combined is machine learning, forming the reinforcement learning, forming the modern days robotics design, right? The control part, right? So you may have to have good GPU, good CPU, maybe also good NPE, okay, neural processing engine, maybe also some TPU. Okay, a lot of processors are involved now. And you need to build a new server on top of this. So always compiler would be on top of this. Okay. So that the new industry will go to, right? And who is number one? Number one right now is NVIDIA. Okay. Number one, NVIDIA. So you need to map your robot control problems. Okay, even LLM, whatever model you have, onto the GPU. That's what the CUDA do, right? So same thing here. You learn the modeling of your robotics, whatever you actually come up with your idea of robot control, whatever, a lot of things. Eventually, you need to map to CPU or GPU or NPU, or if you don't like them, you design your own ASIC, application-specific IC, right? But that's the core part of here. Okay, you learn robotics, you learn the modeling, you have the math, and then what's the next? The next one, you need to find your computation platform. You need to be able to write your own CUDA code. Python, okay. That's if you have to use Python, they are what? PyTorch. Okay, they are also Python Spark for big data. Okay, and also Python TensorFlow. Okay, a lot of package for it. And then there's also one thing, PyCUDA. Okay, to map your Python code onto the machine. Okay, so basically, I'm sorry. Basically, you use the mathematical modeling that you have so far. That actually is describing the control system. Okay, and you draw the schematic and then whatever you do. Okay, and you come up with your robot architecture. Okay, and then you need to map your whole control system onto a set of ASIC. So two-way, you map to an ASIC and you write your own FPGA to realize it. Another way is that, oh, let me map it onto a single CPU or GPU, and on top of it, I run a real-time OS. Okay, ROS. There is a ROS for robots. So they are separate way, custom IC or general purpose programming environment. Okay, these are robot architecture you have. And then these are the block diagram. Okay, you can write it to the best way to support your robot. Okay, and that's a system architecture. And then the control system. Okay, the IO portion. Okay, different IO portion to sense it. Okay. Okay, and then this actually is the environment, but the real control scheme, there are four kinds of the control scheme. Okay, hierarchical, reactive, and behavioral based, and the hybrid. Four kinds. Okay, so hierarchical is the most general one: sense, plan, and action. Okay, but hierarchical has a big problem, right? What is the hierarchical big problem? This sense, plan, and action measure. Okay. Okay, I'm sorry. There's a big problem with this hierarchical things. Okay. So basically, let's look at the so-called ship. Okay, destroyer ship. Right, destroyer ship. It always comes with the white-headed closing complex system, right? And they are also radar, okay, whatever radar, okay, on the ship. Okay, what happened is there is a missile coming in, okay, coming from some direction. So this guy sends, and then whether you will counter attack or not, there is a planning system you do. So you do calculation, right? So if this missile come in and then it actually go back, or some airplane come in and go back, you will not shoot, okay? But you will spend your CPU time to do calculation. So there are certain war that we lost some destroyer because some Arabic country do come back and forth, come in and get out, come in and get out, and then your CPU keep going, and then it just third try or fourth try just hit, and then you never fire any bullet on it. Okay, so that actually caused some value. So this hierarchical sense plan control loop have one major drawback is that the planning takes some time, especially if you put AI on it, it takes some time. But this problem was solved because AI actually nowadays is so powerful. The CPU is so powerful. So the computer become bigger, and then this planning part become shorter time. Okay, it becomes shorter time. So that's the current status of the hierarchical control loop. Okay. Second one is the reactive. Okay, so you sense, you react right away. So this one usually the closing combat system, the gun is in this system, but you will waste your bullet. Okay, you will waste your bullet in this case. But the reaction time is faster, right? You come in, sense, fire back, okay, and then you will shoot a rocket or airplane down. But sometimes it's it will be a false alarm, but you will waste your bullet, okay? That's number two, reactive. Third one is behavioral based, okay? So this is behavior based. We have the two loop, okay? Right here, it shows two loop. So two loop. Or why is that? It's actually, let's look at this. If you have a turtle in the maze, okay, and you are running it for the auto running, okay. So okay, let's assume that this is an iRobot, the vacuum cleaner. So you hit the this one, you may have a plan A, you turn left, plan B, you turn right, okay. So you will have different loop performing different control. But eventually you will have an arbitrator to decide that this time I would like to go right. So the arbitrator can be a random number generator, can be a path optimizer, or some different controller, extra controller. But this one actually is providing more than one plan. This one is one plan, but this one actually more than one plan. So you can actually combine number one, number two, or several different plan, but use an arbitrator to decide it. This is called behavioral based. Is that okay? Last one is called hybrid, deliberate, and reactive. Okay, this one is the combining the number one and number two into a plan. So how does this work? This one usually is like, okay, if the missile coming in at 3 times of the sound speed, okay, then we just react. US team bullet doesn't hurt, okay. If the missile coming in is a sub the sound speed, okay, then it's slower. Then let's use the computer to calculate, okay. So that actually is a combined system. If we use the destroyer's case as an example, so these 4 type of control, they all been used in the weaponry system, okay. So there's a different category of the control, okay. And why am I knowing this so much? I served in the Navy for 2 years, okay. In a submarine ship and also the destroyers, and I'm a weaponry officer. So I control those closing combat system, also the torpedoes, okay. So this different loop and control, I do play those toy before, okay. I do play those toy before. Okay, so this one deliberated paradigm. The bottleneck is the planning part. Okay, and nowadays the planning part changed from traditional algorithm to AI, makes things worse. Okay, so the AI quality and computing speed is actually the bottleneck. Okay. By the way, my son just come in to say bye-bye to me. Okay, he will return to Berkeley, but he recently got an internship offer from NVIDIA. Okay, so he was starting to do his deep learning algorithm intern at NVIDIA. NVIDIA need a lot of people doing those people to write the LLM and also deep learning algorithm. Okay. So this our robotics course, if you learn those Jacobian metric well, it can also be used in the machine learning, mechanical control, also in robot. Okay, so it's very widely used material. So you must try your best to really master the Jacobian metric. Okay, and those whole set of the mathematical modeling tool. It's not just for robotics. Okay, it can be applied for any system that will require differential kinematics. Okay. Okay, so another type of the control is reactive paradigm. Okay, so this one, no war model. What is war model? Okay, this one, let's actually talk about it. War model, okay. When you sense the environment, okay, this one, you will sense the environment and build the war model. What does this mean? You have a ship, right? And then you have the radar. So you sense like multiple source of the attack, multiple missile coming in. Okay, and then this radar system, control system will build a model of the war. That means that it's an environmental model. Who here two missile, here one rocket, here one submarine ship coming, and then I as a ship, which one is the most threatening missile? I will target it and take it. Okay, that actually is the idea of the Israel's Iron Dome. Okay, Iron Dome. Okay, I'm not supporting any part in the war. Okay, I just talk about technical things, so that you will actually update the war and then update the plan. Okay, that actually is what you need to build a war model. War model means that, okay, what is the object who is moving, coming closer to us? Okay, that's war model. So we would take the target after careful planning. This one is not, okay. This one, we don't build a war model. It's a sense and act. So no planning. I don't know where they are. I don't care. I just shoot back. Okay. It's actually different. So it's faster, but sometimes you are wasting your bullets. Okay. And then next one is comparison. Okay, speed of response, reactive is better. Okay, in terms of the predictive and completeness of the war model, the deliberated system is better. And usually this one is a symbolic. Okay, symbolic means that you have your knowledge system and maybe using AI to control it. Reactive usually is just a quick response. Okay, it may be just a digital filter or some simple reactive decision will be made. Okay, and they are comparison between these differences. Okay, next one is the behavioral based architecture. Okay, so this one actually treated the whole system like an objective already the programming. Okay. So you may have push, go through the door, approaching object, and follow a wall. 4 different methods for the robot. Okay, and you do one of them based on the arbitration. But during the computation, those 4 algorithms keep running by themselves. Okay, so this we call it a behavioral-based architecture. So your CPU will control. Right now, you actually already hit the door. You need to decide whether to push the door or you actually go through the door. That is done by the arbitration. Okay. And then arbitration, of course, need to have some planning, and there may be some gambling. Okay, go through the door, you may be hit by another robot, and you may be destroyed. Okay, push the door, you may not be able to complete the finish. Okay, so that arbitration sometimes needs some smartness to make decision. Okay, and sometimes the arbitration decided by human. Okay, if you turn back to the human mode for the operation. So you just try to execute different behavior and then work on the arbitration. Okay, this one and that. Okay, so behavioral architecture. So different behavior-based architecture have different approach to provide arbitration. Okay, so hybrid system, you will build a model and use for planning. Okay, but sometimes you don't do it because you want to fire back right away. Okay. So these are the basic 4 types of the model. Okay, 4 types of control model. Okay, we are up to here. Let's see this one. Choice of the robotic control architecture. So which one you should use? Okay, this is a big topic. So you depend on the environment. Okay, depend on the environment. Whether your environment is noisy, you are in the battlefields, okay, or you are actually just in the golf course. Okay, that decided which way you should do. Okay, I think in the golf course and you have autopiloting car, I don't think you would like to use the reactive, right? It is out of control. Maybe a wrong shooting, then it's not good. Okay, so if it's more less dangerous environment, you don't do those kind of quick reaction. Okay, you would allow the computer to finish. So something like that. Okay, you actually the choice of computer control architecture really depend on your working environment. Okay, not really always pick one over the other. Okay. And here we have different way to do it. Deep learning neural network. Okay, so this guy is NVIDIA. Okay, DSP microprocessor base. This guy is ARM. Okay, and ASIC. This guy is Linux. Okay, digital filter. Okay, this is Broadcom. You actually design your custom filter by yourself. So there are several different ways you can do it. Okay. And your modeling need to decide which one I would like to make on it. Okay, they are economical decision, also technology decision, also time decision. Okay, schedule decision. Okay, the system type you have parallel paradigm and serial paradigm. Okay, and another system is event-driven and synchronous system that you actually have a clock-based system. Okay. And you may have an operation system if you choose to use microprocessor, okay? And this is robotic operation system. You can search internet for this ROS, okay? Okay, and criteria, okay, here there are several criteria. I don't go over it, okay? Criteria usually response time, environmental model, and internal state, okay? So like this robot in the maze, you need to build up your environmental model. It can be spatial, okay? Like map or space. It can be object, okay? Like chessboard, okay? Like chessboard, which are the stone on the chessboard. It can be depending on the action, okay? Missile flying over, okay? It can be self or ego, okay? That actually some AI, you allow it to store the prior precision. Okay, it makes sense and decided by itself. Okay, these are different environment model. So smart control is that in the past, you sense and you plan. And the planning part can be traditional algorithm. Now it's different. Now you would have the whole machine learning and deep neural network to learn. That's modern days AI control. Okay. So if you don't have this AI part, it is still robotics. Okay. Robotics can be traditional and without it. But we talk about this one with AI that becomes smart robotics. Okay. If you have the AI control, it becomes smart robotics. But it's a traditional robot arm has nothing special. It just have a few degree of freedom movement, and then you can sense and react. Okay, if you like, you can do that. But you can also acquire the machine learning to make better decisions. Okay. Okay, and then you may build this is a case study. Okay, case study means that this one is simple. So you may build a temperature sensor. Okay, so they are actuator. Okay, actuator means that you will turn on the heater. Okay, or fuel the furnace. And there's a controller set point that is the desired temperature indoor. So you may program your indoors temperature nowadays maybe 68 degree F, right? That's actually the set point. And then you may have a sensor. Sensor will sense current temperature indoor. Maybe right now it's only 55, okay? But you do have some disturbance. Maybe your little brother just opened the door. Your mom just turned the window open because that the kitchen is overheated. Okay, whatever. So this is your whole system, including all of the factors that may be changing your temperature. Okay, you need to model them in before you decided how to provide the control. So you do have such a feedback loop. Sensor sense the temperature, pick that to compare with the set point. Okay, your sensor right now maybe sense is only 55 degree F. Your set point may want to be 68. So there's a difference. Then you need to turn on the controller to control your temperature control. Okay, maybe heater. Okay. So that's case number one. Okay, it's a simple feedback loop. Case number two, automobile speed. Okay, by the way, this controls loop can be implemented by ASIC or microprocessor or a different way. Okay. Second two, automobile speed control. So you drive the car, you want to control the speed. So there are gas pedal position, fuel to engine. Set point is desired speed, mile per hour. Sensor is a speedometer. Okay. Disturbance is a wind or other car. Okay, so these are different factors. So you draw your schematic, okay, whatever, and create a block diagram for how to control it. Okay. And then you need to know about all the control theory terminology. So this is more like control engineering in EE or mechanical engineering. Okay. Okay, and then once you're done with the loop, you may choose general purpose processor ASIC or ASIP. ASIC is Linux, okay, Linux programmable gate array, okay. ASIP is application-specific processor, so it's some sort of DSP or some sort of processor, but not CPU like ARM or x86. Okay, that's called ASIP. So these three approaches are different. Okay. So you may have the ASIP architecture and the design flow and go hardware software co-design. Okay. Hardware software co-design, we have MIT and Berkeley. They both have the X major, EE and CS major. Okay, it's a hardware software co-design. Covering both EE and CS. Okay. and you have DSP, ASIC. These are design flow. Okay, if you want to choose the middle one, ASIC. And these are design flow of that. Okay, how to generate the design. And here, your automatic level, you can use a distributed multi-processor or programmable gate array, okay, or finite state machine or functional level server. So different intelligence level and different hardware difficulty, okay, and different autonomy level, okay. And also choose something within your economical plan, your pricing range, okay. And these are the behavioral model and hardware implementation, and use a spiral design, okay. Okay, and then analyze the design and hardware software co-design, okay. Again, hardware software co-design. Okay, and then you have the whole design chain for hardware and software. Okay, so today I roughly go through this control. Any questions so far?
It's okay.
No, sir, it's good.
Any question?
I'm good, sir. We are good.
So far, okay.
Yes, sir.
Okay, so this one we introduce over the control. Okay, this is chapter, lecture 12 for robot control. Okay, so we work on the robot arm, okay, and talking about workspace and joint variable first, right? And now we work on the whole control loop, including the sensor and feedback and set point control, okay? So those are actually computing more the back end, okay? The image and vision and servo, these are for this is lecture 11, these are for the sensing part. So this portion, I don't spend too much time because it's actually image processing and also video processing is a separate domain, okay? So this one, you build different model, okay? We don't emphasize on this one. Lecture 13, we have dynamic modeling, okay? This one actually is go into detail of the loop. So you need to check is a feedback loop in the appendix C. This is not a chapter, okay? So you talk about different kind of modeling, okay? This one is more difficult, so I think today I'm up to here, okay? Next time I'll talk about this dynamic system. Is that okay?
That's good.
Because your homework is not up to here yet, okay? Your homework is not up to here yet, okay?
Okay, sir.
Any question?
No.
No, that's it for today, okay? And still, if you have question, you are urgent, I still suggest you to go to where?
Facebook.com.
Yeah, my Facebook. I'll react faster, okay? Because I'm not full-time professor, so if you send me through the Louis email, I may check it 2 days, 3 days later, okay? Then that's not the best reaction I can have. So you may feel like, okay, why my professor never responds? Because I never read the email, okay, for those days. Is that okay? Sorry for that.
Okay.
And Facebook, I guarantee you, within 24 hours, I should answer you, okay? Worst case, 24 hours. Okay, and also need to work harder, okay? Because this year's intern is very hard to find, okay? And basically, we learn this robotics because you want to learn some math and also combining the coding skill, like working on more code, right?
Yes.
You go to the interview, but interview now they always like 5 rounds or 6 rounds, okay, going for a long time, okay, before you can land on a good intern. So try your best, okay, try your best. Okay, see you next time, okay, bye.
Yeah, bye.
Okay, see you. Bye.